Hello everyone, welcome to a new video in the series of practical LLMs. In this video, we'll see how we can modify the last output decoder layer of an LLM and restrict it to generate from a fixed subset vocabulary of the tokenizer. So without any fine tuning, just by modifying the last layer of Google's Gemma model, we'll see how to adapt it for sentiment classification and generate outputs only between the three tokens, positive, negative, and neutral. The key here is that we are modifying the last tokenizer decoder layer of the Gemma model that can output from any of the 256K token vocabulary to output from the three tokens positive, negative, and neutral. So that leaves no scope for hallucination. And regardless of the input sentence that might be in any language, let's say Hindi, Chinese, French, etc., the output model generation is restricted to just three sentiment tokens: positive, negative, and neutral. In practicality, we'll just keep a few more tokens like beginning of sequence, end of sequence, pad, etc., that are core to the model. So the final subset of generation between will be between these three sentiment tokens and three or four more essential tokens of the model. This tutorial gives you a good overview of how to look at a model's architecture, and also you learn how to alter the last layer of the model to restrict generation to only a small subset of tokens from the tokenizer. Without any further ado, let's get started. You can find the collab notebook link in the description of this video. Let's get started. Let's first install transformers and bits and byte PEFT library, because we are going to load a LoRa model that is trained on top of Google Gemma and do our exploration. But at the end of the day, the tokenizer is pretty much exactly the same. So no changes in how you operate, but just the model architecture might differ a little bit. So we are using A100 here. The biggest reason is that I don't want to load it in 4-bit, because moving the model from GPU to CPU is complicated if you load it in 4-bit. That's why I'm using A100, which can directly do inference on the model, and we can comfortably move it from CPU to GPU, etc. Because since we are going to change the language modeling head, we need this feature where we want to be able to easily move the model from CPU to GPU, etc. You can find the Telugu LLM Labs link here that we are working on, which is open source models for Indic languages. And you can find both of our links, Ravi and Ramsri, myself, who are working on this. Let's run this cell as well, where you get your Hugging Face token. And let's actually run this cell where we download our model as well as load it, both the model and tokenizer. Here I am loading a instruction tuned model on top of Gemma, Google's Gemma 7 billion. And this model is instruction tuned on about 80k instructions that are translated form of alpaca, translated into Telugu. Since Gemma is pretty good with Indian languages, most Indian languages, you can actually train and do instruction tuning without expanding the tokenizer. But the concept that we are going to discuss, which is removing the tokens from the last layer of language modeling head, that is pretty much the same no matter which model that you use. So you can apply this for any base model, etc. But note that there are some quirks that we are going to discuss, which is essentially the individual tokens that are present in your tokenizer should be able to do the classification that you want. Now that the model is loaded, let's get into the next section. So basically this model is trained in alpaca format, where you have this baseline instruction, then you can pass in an instruction and optional input, and it will generate a response. Let's run this model and see. Here I'm asking it to generate a children's story on the topic of elephant. Let's run this. So here we are doing a simple inference first to see that the model is working well. Then we are going to delve into how to change the tokenizer, etc. So at the end of the day, simply this instruction is going to come in this place. Since there is no input, this will be empty, and response will be generated here. So as you can see, this is the format. BO is beginning of sequence, below is an instruction. Then write a children's story on elephant. That is what I have it in Telugu, and it gave a response in Telugu as well. Simply, once there lived an elephant named Maya in jungle, something like that. ఒకప్పుడు ఒక మాయా అడవిలో ఏనుగు అనే అందమైన జంతువు ఉండేది. Anyways, so as you can see, it generated some text for this. Now let's try to do some classification with the original model. By original model I mean this is just an instruction tune model, so it can take in the tokenizer is of 256k vocabulary. Then the output decoding layer is also 256k. What that simply means is the text generation will happen token by token, and the model generates 256k probabilities at every step, and we are going to take the token with the highest probability at every step. So that's how the model will generate. So it is going to generate 256 probabilities at every step of text generation to get one token. Nevertheless, let's try to see. We have changed the instruction and input like this. Classify the following user input into one of positive, negative or neutral. Let's see in Google Translate what this is. Okay, any language to English. So ఈ రోజు డెలివరీ చేసిన ఆహారం పాడైంది. సో ఫర్ ఎగ్జాంపుల్ అజ్యూమ్ దట్ it's a food delivery app, and the sentence is the food delivered today was spoiled. That's written in Telugu, and we are giving an instruction and giving an input, so it will just plug into this alpaca format. Let's run this and it will be very clear. Awesome. So this is the full instruction till here, and this is the output, and the output says negative and end of token. So basically negative is in Telugu, so negative basically, that's what it is. So at the end of the day, you are going to generate something, but although you asked it to give output in positive, negative or neutral, it might output in regional languages, or since it is doing decoding between and finding the highest probability from 256,000 tokens, although it might get it correctly, it might hallucinate sometimes, and there are all these things that can happen. Either it can output in regional languages, like at the moment we trained it to output it like this, but I'll just show you. By the end of this video, we'll see how to just take the same model, do not change anything, just change the final architecture layer, where you remove all the tokens and keep only a set of few tokens, and automatically this whatever same input that used to give Telugu negative will give proper negative in English. Similarly, let's run through another sentence which is a positive sentence. So it gave positive. Let's see the output first. Positive. So and the sentence is driver చాలా సురక్షితంగా మరియు బాధ్యతతో ఉన్నాడు. So the driver is very safe and responsible. That is what it means. And neutral doesn't work that well with Google's Gemma model itself. Even if you take the base Google's Gemma instruction tune model and you give something like Raju is father of Sham and classify it as positive, negative, or neutral. We expect it to give neutral, but it says something like, since it is a relationship and you're happy with that, it is a positive sentence. Similarly, when you say you went out for a walk, it says since you're getting exercise, it is a positive sentence. So the Google's Gemma instruction tune model, or the base model itself, struggles with this token, to get neutral correctly. So that's one quirk of it. But nevertheless, for any other standard model, if it's well fine-tuned, you can basically strip off all the tokens, just keep these positive, negative, neutral tokens, and you should be able to do the classification. Let's move ahead, and we will see one interesting thing. Now it is doing decoding between 256k tokens, and we are getting the highest probability token. But what we want to see is, instead of, right now it might be generating 10 tokens, and positive might be 5 or 6 tokens or 10 tokens itself. It's not single token. So if you want to do just single token generation and use it as a classification model, we need to see whether those single tokens are available or not in our tokenizer. So let's open our tokenizer.json. And the most important part for us is this vocab, where you have the token and its corresponding token ID. So here we want to see, so each one is a single token. First we'll see whether there is a token for positive. Okay, there's one underscore positive, there's positive, there's capital P and positive, there's one full positive that is completely capitalized letters. Similarly, let's see, so you can see that this is 166788 token. And similarly, let's see whether there is negative. There's plain negative and capital N and negative. Awesome. Then let's see if there is neutral. Neutral. Awesome. So at the end of the day, there are some variations of the tokens that we are looking for. That's good. So let's try to iterate through the 256k tokens and just collect all the tokens that are either positive, negative, or neutral. If you're looking for advanced, you can even strip off underscore in front and find them as well. Let's run this and it will be very evident. Awesome. So here I also added, since I want to keep the model performance and standard tokens as it is, I just kept the first 4 tokens as it is. So pad token, end of sentence, BOS, unknown, I just kept them as it is. So here is where I kept the first 4 tokens. Then I'm iterating and printing and collecting the rest of the tokens that have anything to do with positive, negative, or neutral after lowering the token. So that means even if we have complete capital negative, or complete capital positive, or just P positive, still we are matching and printing them, because we don't know which of these really and completely captures the positive aspect of the sentiment. So let's collect all of this. And like I mentioned, if you're looking for advanced ones, you can even check underscore positive, underscore negative, underscore neutral in any variations as well. But for simplicity, I'm just collecting these. So now I just have 12 tokens, and instead of 256k tokenizer decoding at the very end, I want to strip the last language modeling head and just keep only these 12 tokens. So whatever my model generates, it will only generate between these 12 tokens. That's what I'm going to do. But before that, let's do something. Let's look at the model architecture. So since this is a LoRa model, we have some more wrappers, like There's a base model, LoRa model, then there is Gemma for causal LM and Gemma model. For example, if we just to take Google's base Gemma model, it won't have all these layers, but rather like something like Gemma for causal model, Gemma model, and it won't even have these LoRa dropout and LoRa. These will be absent as well. But the most important thing that you need to understand is this model has an embedding layer in the beginning where it can, any text that you give will be tokenized, and it will take the token embedding from this 256k lookup table. So it's almost like each token has an embedding dimension of 3072, and this is total token count into 3072. This is what the input would be. That means it will, whatever text that you give, it will draw the 3072 embedding vector of the token from this lookup table. The most important thing for us is the final layer actually. So the final layer is a language modeling head that goes from, the embedding vector of the tokenizer 3072 to output features, that is 256k tokens. And our goal is to strip this such that it becomes 3072 and just 12 that we have filtered. As you can see, just 12 here. Let's see how we can modify this model to do that. Now before that, let's do token mapping, because what's happening here is if we are just keeping 12 tokens and we are going to just output between 0 and 11, that is 12 tokens, we need to store which tokens we kept and which the ones that we discarded. So essentially if we just keep a tab on all the tokens that we kept, that's good enough for us. So this is the mapping. So the first 4 tokens are kept as it is, then 3187 token is mapped to 4. So essentially 3187 is this. So 3187 is mapped, that is negative token is mapped to token ID 4. This is token ID 5, 6, and this will be 11. That is what we are storing here. That's it. We are storing this because in the final layer, when we are stripping out all those, for the weight matrix 3072 matrix, for that corresponding token, we need to get the right weight matrix and plug it in. That's what we'll be doing. But this is where we are altering the embedding layer. So we are getting the last embedding decoded layer, that is the language modeling head. Since it is multi-layered, as you can see, nested within this base model, and then you have language modeling head. We are just, going to model. We have model, then we are going to base model, and within that there's another model. Then there is a language modeling head. This path will slightly differ if you don't have the, LoRa configuration that we have. It will become very simple, probably like model.base model.language model head, something like that. If you just take straightforward instruction tune model of Google's Gemma, etc. Since it is LoRa model PEFT configuration, it is, few layers down. That's it. So this, we are getting the language modeling head, that is the last embedding decode layer. Now we are creating a new embedding decode layer because we want to map from this, which is 3072, and this dimension was previously 256k, but now we are just making it to the length of tokens and IDs, which is just 12. So 3072 and 12, that is the dimension of this linear layer that we are altering. And we are iterating through the token IDs. We are getting the new token ID, and to this last embedding layer, we are changing the weight matrix of that corresponding index. So this is almost like new last embedding layer. um, for example 5, the there used to be some other 5 token, for example, yeah, so it used to point to 5 is this token, so 0 1 2 3 4 5. So it used to point to the weight matrix of mask. So now you need to go ahead and replace the weight matrix of mask with the weight matrix of this original ID. So instead of 5, which points to weight matrix of mask, you need to get the token ID weight matrix of 35202 and plug it in. So that's what we are doing here. And once that happens, we are going to change the model base model language model head, that is this. So we are getting the old embedding layer. Now we are creating a new embedding layer with new dimensions, and we are updating the weight matrices to point to the correct ones. And now we are replacing the embedding layer with the new embedding layer. So what does this do? After this happens, if you see the output, you will see that the language modeling head is not anymore 256K, but rather just 12. So we have even lessened the parameters heavily here, and whatever output generation happen will only output these tokens and nothing else. Now let's just create a reverse token ID mapping, because we just need to store all the modified tokens and all those, since we are altering the weight matrices. But instead of this 256K, where previously all these things were there, now this is the new mapping where there are only 12 tokens, and first token is pad, EOS, BOS, unknown, and the fourth token is negative, fifth token is positive, neutral, negative, full caps, etc., the ones that we collected. This is amazing. Now we have reduced the tokenizer. Now we are going to do something very interesting, which is we are going to run through the same prompt. ఈ రోజు డెలివరీ చేసిన ఆహారం పాడైంది, దట్ ఈస్ the food that was delivered today was bad. So the same thing. For example, let's go through. Yeah, so this one, when we ran the food delivery one, we got negative in Telugu and an end of token, and this one we got positive. So we ran driver is safe and we got positive in Telugu. Now let's see, just with the altered tokenizer, what are we going to get. So this is the exact one that we ran, and pretty much everything is the same. But right now, since all of these are one tokens, that is positive, negative, neutral, etc., you can just generate one token and that should be good. Let's see. Let's run this. Amazing. We got positive. Previously we got Telugu positive, but now we got English positive, because we have stripped out all the tokens except these 12 tokens. So whatever the model generates should fall only in these 12 tokens. Now let's comment this. Let's try something else. Yeah, the other one, the food that was delivered today was bad. Awesome, it is negative. And let's say run this cinema. So this means the movie is not great. Let's run this. Negative. Awesome. So as you can see, it works very well. It's not very good with neutral, and I believe that has nothing to do with our fine-tuned model, but rather even the base Gemma model doesn't get neutral very well. Let's just try this. I ate food in the afternoon. I think this works well with neutral. But this works well. I ate rice and dal in the afternoon. That's what this means. But nevertheless, you have seen how you can strip the tokenizer down and reduce the output tokens to only fixed number of tokens that you want to keep, and this is amazing. Now the best thing is that you can save the model just like any Hugging Face model. Model.save pre-trained into a folder, and it will be saved with the new architecture. So basically you'll have fewer parameters, so less size on disk and less GPU RAM. All of these, you get all of these benefits. And again, if you're smart enough to not use some embeddings at all completely and remove, you can even play with this embedding tokens size here and reduce the model size, kind of like make multilingual models monolingual or just bilingual by just preserving English and Hindi tokens plus few other tokens, etc. So these are some of the experiments that you can do. And again, you can merge the LoRa layers. So you can basically merge the LoRa layers and uh, make it like a regular Gemma for causal LM model as well, instead of loading it as a PEFT model and using it. So you cannot do all of these things. I made a little summary with the help of Claude and edited it so that you can go through all the things. So simply, in the original model, just to summarize everything, in the original model, the last embedding decode layer, the language model head, is a linear layer, and the dimensions are hidden size by vocab size. So 3072 by 256K in our case. And just a simple example, if there is 768 by 50,000, now what you're doing is you're removing those 50,000 and just keeping like just 12, so that now those connections are 768 by 12. But the important thing is that you are fetching those weight values for the corresponding weight matrix that is relevant to only the tokens that are preserved. So remember that. Now again, we are preserving everything, that is which tokens were mapping to which, and how is the new token map, etc., so that we can do all the decoding of tokenizer as usual. Now the biggest thing is that the model will only output probabilities for only this subset of tokens, that is 12 tokens, and that's it. You have reduced computational overhead and reducing hallucination by just forcing the generation to be only among these tokens. And we replace the the model's language model head with the new embedding layer that we have created. So this perfectly summarizes: by creating a new last embedding decoder layer with reduced dimensions and copying the weights of the subset of tokens from the original layer, we are able to trim the model to focus only on specific tokens of interest, thereby reducing the computational overhead and adapting the model to our specific use case. So simply this means you can even try and see any classification. For example, if you want to classify an article customer support request into sales, marketing, or tech, etc., also you can try this out. Just try and see if there are single tokens that match to your criteria. For example, let me see if there is sales. Yeah, I mean underscore sales. Great. There'll be, yeah, there's sales as well, right? So token. So you can do all these things like sales, marketing, and tech. Again, you can see technology and yeah, plain tech as well. So you can play with all of these. And more than being a straightforward model that you can use for classification, this helps quite a lot for you to understand, because now you're playing with the embedding dimensions as well as modifying the tokenizer and tokens, and also the model language model head. I hope this tutorial gave you a good chance to look beyond just the tokenizer and play with the model architecture a little bit. Thanks for watching. I'll see you in the next video.